Okay, 5.3. We used the addition rule last time to compute the probability of or events. Now, we're going to describe a probability rule for computing the probability of and events. In other words, that both events occur at the same time. Okay, event A and event B happened. But before we can do that, we got to discuss the idea of independent events. So two events are independent if the occurrence of event E in a probability experiment does not affect the probability of the other event. Two events are dependent if the occurrence of E affects the probability of F. So think about flipping a coin twice. Does the fact that you get a head on the first toss have any effect on the likelihood of getting a head on the second toss? Those are independent events. Tossing the coin the first time does not affect the outcome of the second time. So look at these questions. Suppose you draw a card from a standard 52 card deck of cards, and then you roll a die. So your two events are you draw a heart and then roll an even number. Are those independent? Okay, whether or not you draw a heart, does that have any effect on what number you roll on that die? No. So yes, these are independent. Suppose two 40-year-old women who live in the United States are randomly selected. Are the events that the first woman survives a year and the second woman survives the year independent? Well, these are randomly selected women from the entire population of the United States. So it's pretty certain that one of them has nothing to do with the other. So yes, those are independent events. As opposed to look at example C. Suppose two 40-year-old women live in the same apartment complex. Are the events that the first woman survives the year and the second woman survives the year independent? We can't say that. I mean, they could be, but we would have to state no because they might not be. What if the pipes are contaminated in that building, right? Or any kind of contamination in the building. Okay, what if there's a serial killer loose in the city that's targeting old women and they live in the same place? So no, those events are not independent because the probability of one happening might affect the probability of the other one happening. So caution, be careful. Disjoint events and independent events are different concepts. Okay, two events are disjoint if they have no outcomes in common. That is, if knowing one of the events occurs, then we know the other event did not occur, right? Because they have nothing in common. Independence means that one event occurring doesn't affect the probability of the other event occurring. So it could also occur or not. But if they're disjoint and we know that one occurs, we know the other one does not because they cannot occur at the same time. Okay, does that make sense, the distinction between those? Okay, well, suppose that you flip a fair coin twice. Okay, what's the probability that you obtain a head on both flips? That is, a head on the first flip and a head on the second flip, right? Well, let's look at that a little bit. Here, what would our sample space be? We're flipping two coins. So we could get heads. We could get, why do I keep doing that? We could get heads on the first one and then tails. We could get tails on the first flip and then a head. Or they could both be tails. Okay. So here's one way that we could figure out the probability, right? Which is, what's the probability that you get heads on the first flip and heads on the second. It's 1 out of 4 possibilities. Okay? So look at what our rule states. If they're independent, again, we got to know that. If they're independent, when we want to know the probability of getting let's say, a head on the first one and a head on the second, notice what this is saying. Hey, we can just multiply them. What's the probability if you're flipping a coin, you get a head on the flip? Okay, you're going to do it again. What's the probability you get a head on the flip? Oh, hey, notice what that is. Okay, so our multiplication rule is for and. If I want to know the probability that one thing is going to happen and also the other is, tells me I can just multiply the 2 individual probabilities. For example, okay, the probability that a randomly selected female, age 60 years old, will survive the year is 99.186%, according to the National Vital Statistics Report. What's the probability that 2 randomly selected females 60 years old will survive the year? Okay, so it tells us that the survival of the first female is independent of the survival of the second female, right? And we know what that probability is. This is 99.186% written as a decimal. So if we want to know what's the probability that the first one survives, I'm going to shorten that to say lives, and the second one lives, right? Here's what our notation would look like. The probability that the first one lives and also the second one lives, that's the same thing as saying, okay, that 2 of them, right, that they both survive. Here's the probability that the first one survived times the probability that the second one survived. So let's multiply that together. Notice you could just say 0.99186 squared. And as I put that in my calculator, that is what I'm going to say. So 0.9838. Rounded to 4 decimal places. Okay, if you have 2 independent events, you just multiply each individual event to find the probability of both of them happening. Okay, let's do another one. A manufacturer of exercise equipment knows that 10% of their products are defective. They also know that only 30% of their customers will actually use the equipment in the first year after it's purchased. If there's a 1-year warranty on the equipment, what proportion of the customers will actually make a valid warranty claim? So in other words, what we want to know is, what's the probability that their product is defective and then the customer will make a claim, right? This is an and. Both things have to happen. You don't make a claim if your product's not defective, right? So it has to be defective. And if it's defective, what's the probability that you'll make a claim? Okay, so 10% of their products are defective. 30% of their customers will actually use the equipment in the first year. So what's that? 0.03, right? So 3%. Okay, and of course, they had to assume that defectiveness of the equipment is independent of the use of the equipment. Okay, we can extend the multiplication rule for 3 or more independent events, just like we did the addition rule for those disjoint events, right? So if you have multiple events, you just multiply however many that you have. For example, the probability that a randomly selected female age 60 years old will survive the year is this again. Okay, what is the probability that 4 females will survive? Okay, so that's the probability that the first one lives, and the second one lives, and the third one lives, and the fourth one lives, right? That's what it means if you want the probability that 4 of them will live. Oh, then the first one and the second and the third and the fourth live. So it's 0.99186 times 0.99186 times 0.99186, blah, 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 4 times, all right? So 0.99186 to the 4th. Or 0.9678. Okay. Okay. Usually, probabilities that involve the phrase at least use the complement rule, because the phrase at least means greater than or equal to. For example, a person must be at least 17 years old to see an R-rated movie. This means that the person's age must be greater than or equal to 17 to watch the movie, so people under 16 cannot, the complement, not watch the movie, right? Okay, so the probability that a randomly selected female age 60 years old will survive the year is this again. What's the probability that at least one of 500 randomly selected 60-year-old females will die during the course of the year? Oh, notice all of a sudden we're wanting to know the probability they're going to not live, right? So let's start with just saying, well, what's the probability that one of them will die? Let's look at that. Okay, what's the probability that one does not live? Okay, it's 1 minus 0.99186, right? Whatever that is. Okay, what about at least one of 4? So what's the probability that 4? Oh, no, I don't want to say exactly 4. Well, yeah, let's start with that to get us an idea. Sorry, that was actually a good idea. Okay, what's the probability that 4 do not live? Let me get this number up here, that 1 does not live. Okay, 0.99186. Okay. Is 0.00814. Okay, so what's the probability that 4 of them do not live? It's 0.00814 to the 4th, right? The first one dies, the second one dies. Okay. So now let's look at, let's say, what's the probability that at least 4 not live? Okay, so one thing we could do with this is say, okay, we would find the probability that 1 dies and add the probability that 2 dies and add the probability that 3 dies and add the probability that 4 dies, right? Is this what it means to say at least 4 die? Well, find the probability that 1 of them died, then find the probability that 2 of them died, find the probability that 3 of them died, find the probability that 4 of them died, and add it all together. Okay, so we could do that. Okay, we're talking about 1 out of 500. Do you really want to do that? So another thing we could do with our at least, so probability at least 4 die, is say, well, it's 1 minus the probability that they live, right? So this is the probability that 1 lived, 2 lived, 3 lived, and 4 lived. Here's our pattern. However many you're talking about goes on your exponent. It's this same idea that we had before of repeating this, extending this multiplication rule to multiple things. Okay? Now, in this, we've already done the 1 minus, right? That's that they not live. 1 didn't live, 1 didn't live, 1 didn't live. Then I'd have to do it again for 2 times, 1 time. So here is just, we're going to say that they all lived and take it away from 1. So if I want to know the probability that at least 1 of 500, right? Probability at least 1 of 500 die. It's going to be 1 minus 0.99186 to the 500. Okay, let's look at that. 1 minus 0.99186 to the 500 power. So 0.9832. Okay, there's a pretty high chance that at least 1 out of 500 60-year-olds is going to die. Okay. Even though each individual one, there's a really high chance they're not. Okay, so did this pattern for the formula make sense though? Okay, so my 500 is going to go here. It's always going to be 1 minus, and then the probability that it does happen. Okay, this should say at least 1 out of 4. Okay, 500. It's always the same. All right, let me know if you need any help with that. And then finally, here's just a summary of our rules. Okay, so first of all, remember the probability of any event has to be between 0 and 1, right? All probabilities are between 0 and 1 inclusive, including 0 and 1. No negatives, nothing bigger than 1. The sum of all the probabilities must equal 1. Okay, here's our formulas for ORs, and here's our formulas for the complement and the formula for AND. Notice that the or probabilities use the addition rule, and the and probabilities use the multiplication rule, right? This is E or F, and really this is the only rule we need, right? If they're disjoint, we can shorten it, but if they're disjoint, this is 0, so same thing. Okay, here's our complement, and this is related. They don't have the at least one rule up here. Let's add that, actually. Okay, and the and you multiply. So 6. Okay. So the probability of that would be 1 minus the probability of your event happening, whatever it is, the probability it will happen, to the n. 1 out of however many. Okay, probability of at least 1 out of n. All right. Let me know if you need any help on that.